Good afternoon. Good afternoon. Hello. Yeah, last time we had introduced the Bohr theorem, and we talked about the energy levels. We talked about the series of lines produced. There is the Balmer series, the Paschen series. And we saw how they came about. And I remember mentioning that the different series of lines formed can be talked about in a way of how the transitions occur. And according to what we had seen that when an electron makes a transition from any excited states, it comes and lands in the ground state. And this is what we call the ground state. And in the ground state, the series of lines produced are what we call the Lehman series, which correspond to the ultraviolet part of the spectrum. Then we also saw a transition which can be made from any excited state, landing in the first excited state. This is our first excited state. And the series of lines here correspond to what we call the Balmer series. And this Balmer series correspond to the visible part of the spectrum. Then we also saw the second excited state. When electrons land in the second excited state, they produce lines corresponding to what we call the Paschen series. And these Paschen series correspond to the infrared part of the spectrum. So from there, we can come and confirm. We can confirm that transitions have been made, and whenever transitions are made, we get what we call electromagnetic radiation of energy, change in energy, which is equal to the energy level we are jumping from to the energy level we are landing on. So it is from here that we can talk about what we call the ionization energy and excitation energy. Ionization and excitation energies. So, starting with ionization energy of an atom is the minimum amount of energy. This is ionization energy of an atom is the minimum amount of energy, required, to remove its mostly loosely or its most loosely bound electrons when the atom energy is the minimum amount of energy required to remove its most loosely bound electrons in the atom. Or loosely bound electrons, you can stop here. Now, what do they mean by this? if you recall the diagram for an atom, it has positive charges in here. And this atom has the innermost shell. The innermost shell has electrons. And these electrons, after which we have the next, which is the first excited state. Then you have the second, which is the second excited state. If you're to see these electrons, the electrons here can be in the form then we have other electrons here. And so on and so forth. But these electrons which are closest to the nucleus are the ones which have the least energy. Those of us who attended the lesson for gravitation, I remember talking about the sun. Some scientists predict that our solar system is a very big giant atom. When we have Mercury here, Mercury has a small mass and is less energetic. That's why it is easily pulled by the sun closest. Then from Mercury, you have Venus. Venus in the second orbit is further away, but Venus is a little bit bigger than Mercury. So in that sense, you see that this planet, which is closest to the sun, is the one with the least energy and moving with perhaps the slowest speed. And with that reason, these ones which are further away, like now the Earth is a little bit away from the sun. The Earth is more massive than these ones, faster than them, more energetic than them. The same applies to these electrons. The electrons which are in the innermost shell, this is the ground state. Electrons which are in the ground state or in the innermost shell, they possess least energy. That is why we are saying ionization energy is that amount of energy which is minimally required to remove an electron which is in the innermost shell and is loosely bound to the nucleus of the atom. So those electrons which are closest to the nucleus, the main amount of energy you require to do that is what we call the ionization energy. And now, if you're to go and see how these what? Let me take you to another diagram to show you how these electrons look like. You'll find that this one, the next orbit, this second orbit, is what we call the first excited state. Then this third one is what we call the second excited state. Now, in those orbits, we see that higher energy electrons can make transitions from there to come and fill a vacancy that can be left. But now, as you look at them, those different energy levels, when you draw them in form of straight lines, this is how they look like. You will have an energy level in the ground state, like I showed you last time. You will have the first excited state. You will have the second excited state, and so on and so forth. But according to the experimental predictions, we have this ground state energy with a value of negative 13.6 electron volts. So if this is the energy in the ground state, yeah, this is energy E1, where N is 1, energy E2, where N is 2, energy E3, where N is 3. Now, if the electron is to leave the atom completely, then it goes to infinity. So ionization energy will predict that the electron has gained maximum energy, which is energy at infinity. Because all these energies are going to be negative, as we shall see. So the maximum energy is 0. When you're at infinity, the energy you have is what? Is 0. So at infinity, energy you'll be possessing will be 0. So if this energy is 0, this is what is expected. Energy at infinity is 0. So energy at infinity is the maximum. And if an electron acquires that energy, it has left or it has gone out of the atom completely. So minus the energy in the ground state, and this will give us 0 minus a negative 13.6 eV. So finally, the ionization energy becomes 13.6 electron volts. If you're asked to get the ionization energy in terms of joules, then you can say the ionization energy can be got from 13.6 times electronic charge, which is 1.6 times 10 power negative 19. And then when you simplify this with a calc, what answer do you get? That becomes the ionization energy. Someone compute that and get the answer.
(2.176 exponent negative 18).
You get?
2.176 exponent negative 18.
Exponent negative 18. Now, from the definition of electron volt, who knows the definition of electron volt, which is 1 eV? 1 electron what? Volt. 1 electron volt is the work that we do to move what? An electron through a PD of 1 volt, if you recall. Yeah? And with that reason, if that work you're doing is to move an electron through a PD of 1 volt, then it means that the kinetic energy gained by an electron is being accelerated through a PD according to our ionization energy. It means that the kinetic energy gained by an electron, it is being accelerated through, because this is 1 eV, 1 electron volt, it means that when you have 13.6 eV, then this is the same as looking at it in the form that if I have 13.6 volts, then this electron has moved through 13.6 voltages, which becomes 13.6 potential. In that sense, what does this help us? This helps us to get what we call the ionization potential. The ionization potential. So the ionization potential for an electron to go to infinity is 13.6 volts, which ionization potential has the same value numerically, but does not have the same units as ionization energy. So ionization energy and ionization potential have the same value, but different units. The units here in terms of EV, the units here are in terms of volts. This is voltage, the other one is energy. EV is energy, whereas V is voltage. So in that sense, it means that our electron would have moved through a PD of 13.6 volts, because 1 electron volt is work you do to move 1 electron through a PD of 1 volt. Now, if the PD is 13.6, then this electron to have 13.6 EV has actually moved through 13.6 voltages of PD. So, so far we have described what we have called ionization energy, and also we have talked about what we are calling the ionization potential, which happen to be having the same value, just because they have different units, but the value of the numerical value of those findings has to always be the what? Has to always be the same. Now, with that, one can also conclude and say ionization potential can also be called VI, can be attained from the ionization energy out of the electronic charge. It is from here that now you see that with the 13.6 EV we had before, if I divide it by the electronic charge, I will get the ionization potential. which is 13.6. So if you want to get it mathematically, you can arrive at it from here. But if you wanted to explain using science, you'd have said that since one electronic charge passing through one EV is 1 electron volt, and we have 13.6 electron volts, then it means the electron would have gone through a PD of 13.6. Thus, the 13.6 becomes our ionization potential. So that is the first case. The second one is going to be talking about what we call the excitation energy. Those are two different items. The first one has been ionization energy and the potential. Now we are looking at excitation energy. Excitation energy is all about exciting the atom. Yeah. So the excitation energy of an atom is the energy required to move an electron of an atom, which is in the ground state, to any higher energy level or to any excited states. What does that mean? It means you're removing an electron. For assuming this is an electron down here. If I shade this red, I have removed the blue electron. If I remove this electron and I move it up to here in the second excited state, then the atom will have, or the electron will have attained what we call excitation energy. That energy is just enough to excite the atom, but it is not enough to ionize the atom. Yeah. When we ionize the atom, we are ideally making it a point that the electron is totally leaving the atom by gaining what we call ionization energy. But now when the electron leaves the ground state and goes to any excited states or to any higher energy levels, then we say the electron has attained what we call the excitation energy. So if I write down the definition, this is how it can be looked at. So you can have excitation energy in this form. Excitation energy of an atom is the energy required. Is the energy required to move an electron of an atom which is in its ground state to a higher energy level. So you're moving an electron which is in the ground state to any higher energy level or to any excited states. In that sense, we are saying you are exhibiting what we have, what we call the excitation energy. I.e., the first and second excitation energies of, let's have an example. The first and second excitation energies of hydrogen are 10.21 EV and 12.09 EV respectively. So the excitation potentials. So the excitation potential is going to be 10.21 volts and 12.09 volts. Remember also, in this case, in case you want to get excitation potential, Therefore, excitation potential let's call it what? VE. V excitation is equal to the excitation energy out of the electron charge. So that's why I have showed you that if you have 10.21 EV as the excitation energies divided by one electronic charge, the answer becomes 10.21 volts. So the idea is the same as the way we get ionization potential from ionization energy divided by the charge. So with those definitions, we can now introduce some questions and we see how best we can have these questions handled. Unless if someone has a question before I proceed with my question. When did you go to the net? What was happening here? I think the guy came here. You go there expecting. So if no questions. So question says below. What is the position? How is English number? One, two, three, 4, 5, 6, 7. Those are 6. So they can say below is a spectrum of an atom. So this is 0. Why? We are at infinity. So energy at infinity is 0. Then, when n is 1, the ground state, we have energy E1, which is equal to negative 13.6 EV. When n is 2, we have energy E2, which is equal to negative 3.39 EV. When n is 3, this is equal to E3, which is equal to negative 1.51 EV. When n is 4, this is E4, which is equal to negative 0.85 EV. When n is 5, this is equal to E5, which is equal to negative 0.54 EV. When n is 6, this is E6, which is equal to negative 0.38 EV. Now, questions are set like that. Sometimes they can give them in word form when they have not drawn for you the energy levels. But you should know which one is the ground state, which one is the first excited state, and so on and so forth. Let me rub off this at once so that I can have access. So, the question says calculate the frequency and wavelength I check the frequency and wavelength of the radiations resulting from the following transitions. A, n is equal to 4 to n is equal to 2. B, n is equal to 2 to n is equal to 1. C, okay, and they have said in brackets, h is equal to 6.625 times 10 power negative 34 joule seconds. That is Planck's constant. Now, according to our question, we have seen the energy levels. And I remember, electrons do not emit radiation once they're in orbit or in those energy levels. But when they make a transition, they emit radiation of energy, which is change in energy, is equal to HF. Now, the first transition is from n is equal to 4 to n is equal to 2. So you get the energy when n is 4, that energy is negative 0.85 eV. Then we have energy when n is equal to 2, which is negative 3.39 eV. So the change in energy will be the energy of the higher energy level minus the energy of the lower energy level, because the energy of the higher energy level is higher than the energy of the lower one. You see, they are negatives, but the smaller negatives are bigger than the bigger negatives. So with that reason, we shall have negative 0.85 eV minus negative 3.39 eV. What answer do you get? What answer do you attain?
2.54.
2.54 eV. So that is the change in energy. So the change in energy is equal to 2.54 eV. But this change in energy is equal to HF. So the question said we find the frequency and wavelength. So I can make F the subject, which becomes 2.54 eV out of 6.625 times 10 power negative 34. This will give me 2.54 times 1.6 times 10 power negative 19 out of 6.625 times 10 power negative 34. When you compute this, what's the value of F?
So it's 6.134 exponent 14.
Exponent 14 has. They asked also for the wavelength. Wavelength, remember, frequency is equal to C out of lambda. So you know the speed of light, right? Which is 3 times 10 to the power 8 divided by 6.134 times 10 to the power 14. So this is giving us the wavelength. So can you get the wavelength?
Exponent negative.
You get?
4.891.
And we 10 to the power. 10 to the power.
-7 meters.
Correct. Now you investigate for me
Correct.
the second one, which says n is equal to 2 up to n is equal to 1 by finding both the frequency and the wavelength.
Excuse me, sir. Is C constant?
C is a constant, which is speed of light.
Okay.
Okay?
Okay.
Yeah, it is always, because if you want to get frequency, frequency is equal to C out of lambda. Frequency is, let's say, is measured in per second. If I want C, I can get F times lambda. But this is in per second. Lambda is in meters. So meters per second is the SI unit for speed. Hence the equation is true. It comes from Web's.
So with frequency, so with frequency up 2.466 exponent 15.
Frequency is equal to 2.466 exponential 15. Correct.
Then wavelength
1.
1.217 exponent -7.
Correct. Any person with a challenge or wondering how the answers have come about? Okay. So if there is no concern there, I have another question. Now, sometimes they might not give you the energies. Now, they might set a question regarding to the derivations we did last week. If you remember those derivations, look at example 2. It says the energy of an electron is given by, remember the energy we saw, or is given as, the energy was defined as En is equal to a negative m exponential to the 4th, what is over 8 of n squared of h squared epsilon squared. Find the wavelength. Find the wavelength of the radiation emitted for electron transition from energy level n is equal to 3 to the ground state. Now, with this, firstly, they are asking you to find the wavelength. They're asking you to find the wavelength. One, you can derive an expression. Or if you don't want to derive, you can use our formula straight away and get the change in energy, because change in energy would be energy E3 minus energy E1, right? Which energy E3 you do not have. So energy E3 can be got from a negative m exponential to the fourth out of 8 times n squared, h squared, epsilon squared. Because mass of an electron is negative 9.11 times 10 power negative 31, electronic charge 1.6 times 10 power negative 19 to the power fourth. With this, I expect people to have smart calculators and smart heads plus smart fingers, because we need your reaction time. The rate at which you're going to press your calc to get the correct answer is key, because these are very huge figures to deal with. Divide by 8 times the n. N now is 3. This is 3 squared times Planck's constant, 6.63 times 10 power negative 34. But Planck's constant is also what? Squared. Also divided by epsilon. Epsilon is 8.85 times 10 to the power negative 12. And this epsilon is also squared. Press your calculator and confirm the answer. Let me write down for E4. So press the calc rightly. Follow my player. How are you? Now you're going to hear people getting answers. You hear answers people say, and then also check on what you've done. I trust many of you are going to have very different answers. You can't mention the answer, you can write negative 2.442. Okay, negative 2.42 times 10 to the power negative 19 joules, correct? That is from Matov. The second one is negative. The second one, Matov, you're giving negative 1.362 wrong. Press the calc again. Someone else? We are denying, but it's very late. Teacher, I'm requesting that you upload this lesson on the YouTube. My network has been terrible. I barely attended this. I deny. Okay, very sorry. Guys, another answer for the second part. This one gave us a wrong one.
Excuse me, sir.
Mm.
I'm getting 0 in E3, like when I multiply 9.11 times 1.6.
You're getting 0?
Yes.
Yeah.
Yes, that is what I'm also.
0. Okay, after 0, what is the first value?
What do you mean?
After the zeros I've gotten down. What is the first value? Just like you see 2.42 in the first answer.
No, I don't even get 2.42, like when I
That is why
multiply.
That's why I told you. Okay, you divide by EV. No, you don't divide by EV. You divide. No, you're saying you don't get an answer. You don't get even because this is what I expected. Negative 2.170 times 10 to the power negative 18. That is why the answers are always given in EV. Yeah? Those energies are very small. So, according to what we have seen, E1 E3 was negative 2.4122 times 10 power negative 19 joules. Then E1, we have got negative 2.170 times 10 power negative 18. Then the change in energy is supposed to be E3 minus E1, which will be negative 2.4122 times 10 power negative 19 minus negative 2.170 times 10 power negative 18. So change in energy is equal to, and compute. So after getting that change in energy, you can proceed. Remember, change in energy is HF. The question wanted us to get the wavelength. So you go to HC over lambda straight away. And you can see that lambda is equal to HC out of change in energy. Then I want to show you the other method of the derivation. That what if someone decides to go and use the derivation which combines the two energies? But we are continuing. Not training. Bench. Leero ngenda kuyitirawo. Yeah, that's it. Yes, guys. Do you have an answer? Yes, someone has an answer. Change in energy has got 1.03 times 10 power. 27. Impossible. So we'll check your calculator. If you have to compute it at once, it is 6.63 times 10 power negative 34 times speed of light divided by change in energy is 2.170 times 10 power 18 a negative minus 2.1412 times 10 power negative 19. Compute that at once and give me the value of lambda. Then I want to show you the other part. What if I had not used that? And I want to get change in energy as E3 minus E1. And yet I know so in case one is not using this other skill of substituting straight away, you can use this technique of substituting all at once. You should come up with the same answer. So one can use that technique and get the answer. Someone has sent an answer. Let me check. 1.03 exponent negative 7. Wrong. Another one. Someone has another answer. Negative 1 point. What is that one you're giving me? Mamatov, what is that? Change in energy. Finally, go ahead and get lambda.
It's wavelength.
Wavelength. Just know wavelength can never exceed.
Yeah.
Wavelength cannot exceed around -6, -7, -8. When it exceeds, stop work. My time is up. So check the answer. Press the calc and confirm that you all get wavelength as 8.239 times 10 power -8. 8.2395 times 10 power negative 8 meters. Those are the answers. One of the ways to simplify very fast is by first reducing the powers. You square, for example, the powers like negative 19, square it to 4, go down, square there the negative 34, you get a negative 78, 68. You have a negative 12, square it, you get a negative 24. Then first simplify those powers alone. For example, up there you have 19. 19 times 4 is 76. So negative 76 plus negative 31, you get a negative 109. You're dividing it by a negative 68. Also dividing it by a negative 24. So you first subtract those exponentials, then put them aside. Then you can simplify the rest, and then that's how easy you can end up having the answers good. That is why some of you are getting nothing. Some of you say the calculator was giving you 0. It's because you are not simplifying the powers very well. So simplify the powers. This is what I mean. 9.4 times 1.6 power 4 times 10 power negative 31. But you do this in your head times 10 and your calculator. See that? Then divided by 8 times 6.63 squared times 10 power negative 68 times 8.85 squared times 10 power negative 24. You will see that you can handle this with this one, which gives us a negative 93. So the power becomes times 10 power negative 109 plus 90 plus 92. Because this power negative 92 goes up, then this power will be condensed. You see that? When the power is condensed, it is condensed actually to power what? To power negative 17. Now you can simplify this one, and this one, and that one, and then finally attach this power, and this one, and then attach that power. Then after, you have this one also to deal with, then you'll get the answer. Okay, we shall start from there next time. So go over the question again and see how you can manipulate the calculator. That's why I said people have to be patient when we reach this area. There are mega values we need to handle. Otherwise, your calculator will just give you 0. Because 0 to the power negative 78, it is very, 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 very negligible. The calc might even be stopping around 63.